Hello, everyone, and good morning, Singapore. It's a pleasure to be on this stage, and today we are talking about the topic of firmware supply chain security, and it is actually broken, but the question is, can we fix it or not? So I'm Alex Matrosov, and I'm CEO and founder of Binarly. So we are doing a lot of firmware security research, and with me on this research committed Alex Ermolov. He is principal security researcher at Binarly, and he's doing a lot of vulnerability research in firmware, hardware, and all shades of devices.
My name is Richard Hughes. I'm a principal engineer at Red Hat, and I'm the maintainer of FWD and the LVFS.
And I'm Michaelis. I'm the CTO of Immune, and I care about all things firmware and cryptography related. So the firmware and hardware supply chain, what's it all about? So before I start off, for the purpose of this talk, when we talk about firmware, we're talking about everything that comes with your x86-based server or laptop system. And of course, everything, this means, of course, the UEFI BIOS firmware, right? But if you have a server, you have at least a BMC firmware on there, there's whole operating system in there. You of course have the source bridge that runs the dreaded ME, or if you have an AMD system, the PSP, and you have extension cards like PCR cards that come with all their own firmware. So, which begs the question, who builds all this firmware? And some of it's actually built by the SoC vendors themselves, like Intel and AMD. Some of that is just binary blobs that are signed and can't be inspected or rechanged. But some of it is actually open source, right? So the reference implementation of UEFI Tiano Core is actually open source. But it's only a really small part. And these artifacts that are generated by the SoC vendors are then consumed by the independent BIOS vendors, who are actually only pure software vendors on this whole chart. And they take that, combine it with their own proprietary code, and produce BIOS firmware, right? And this is then shipped to the ODMs or the OEMs that will combine it with other firmware from other vendors and flash it on the system and ship it to you. The problem is that when we look at the supply chain for that firmware, it's not as easy as a linear chart because the OEMs have different suppliers. For example, the BMC maybe comes from a different supplier. Maybe you have other cards on there. They have their own firmware, right? So you have a tree of firmware that's flowing to the OEM. And the problem is that not only the firmware is flowing downstream to the OEM, so does the updates for that firmware, right? So if you have a bug, you have to approach one of these suppliers, convince them this is actually a problem, right? They have to fix. They ship an update, and this has to be then consumed by the OEM, packaged into a new update, and then shipped to the user. So this creates a lot of problems, right? First, the slack in the system, right? The time it takes for an update to flow downstream to the actual consumer takes a long time, right? Can be measured in months to years until the update is actually reaching the user, so he's able to install that, right? There's also not much coordination between these vendors, right? There's no like coordinated patch cycles or anything like that. They push the updates. They sometimes not even really inform the downstream consumers, right? So sometimes things are just silently patched. So this is a large problem. This is a big problem. And I mean, consumers also have to install an update, right? And installing a firmware update, for example, on scale on Linux systems can be quite challenging. So what do we mean with this complexity here, right? So we have to have this little example here. So let's say we have a vulnerability in one of these components, right? And vulnerability that maybe when we look at it in isolation isn't really exploitable. For example, it allows us to bypass secure boot, but the code in order to bypass it that's vulnerable isn't really reachable, right? That code can breach as a normal boot process. So the vendor decides, assessing a vulnerability that is not a risk and is not patched, right? So this only means that we just need another bug somewhere else in the supply chain, a completely different vendor that does a completely different thing. But because all of this code is combined in, for example, UEFI and runs in the same security context more or less, it means that I can use another vulnerability that again in isolation looks benign. Maybe it allows me to reach certain code that's normally not reachable, but it's all shipped with the UEFI, so there's not much of a problem. But again, if I combine these two, I can see, as you can see on next slide, I get an actual vulnerability that can exploit it, right, at the consumer. And it doesn't even necessarily mean that this vulnerability is out there and ignored, right, the end-day vulnerability. Maybe there's already a patch out there, but because of the slack in the supply chain, the time it takes for an update to throw downstream, I can, as an attacker, find another vulnerability and exploit it before the update reaches the user. So this is the problem here. Vulnerabilities are assessed in isolation because vendors don't talk to each other. And vulnerabilities have an extremely long lifetime, right? Because vendors either are unable to push patches fast or are completely unwilling to patch because they say, okay, this is end of life. We don't support the system anymore, and security patches are part of the support package. So why do we care about security in firmware so much? The problem is that security is a chain, right? And these operating system-based security mechanisms, they all are based on a working UEFI secure boot or a working a secure SMM code. And again, that depends on a working platform protections like bootguard. So if I'm able to attack the firmware, I'm able to attack everything after that, like everything after that breaks, and everything after includes the operating system, right? The thing that we actually want to protect. So before we go into super detail, how these bugs look like, right, and how vendors actually respond to bugs, let's look at what we can do to fix that, right? So we have to educate vendors about security, right? So we have to explain to them, okay, security is not a matter of whether the system is still supported or not, right? You have to always push these security updates. You have to decrease the turnaround times. The slack in the system has to be decreased. So we get from months to maybe weeks to maybe days until we can actually install an update. We have to increase the transparency. We need more centralization, right? I have to find and have a centralized repository where I can say, okay, for this piece of hardware, what patches are available, right? And how do I install them easily? And in the more long term, we probably want more open source here. So we are less dependent on the vendors themselves. And we can access the source code, right? We can fix our problems ourselves and compile that and patch it on our systems. So we're not longer dependent on the vendors. And maybe we should think about how we build hardware and make it more inspectable. So we don't have to just rely on what we get shipped into our doorstep, but we can also verify that the same we verify our software. And I think the Precursor project is a good example for that.
So I will be take over to firmware supply chain failures. And before I will start, actually, Kai did a great overview about supply chain problems and in general, where it can be failed and how multiple vulnerabilities or vulnerable primitives can be combined in pretty suitable exploit chain. But let's talk about repeatable failures, and actually binarily been discovering multiple vulnerabilities over the year, and it's already disclosed 43 vulnerabilities with actually high severity vulnerabilities, and most of them it is SMM privilege escalation or memory corruption vulnerabilities. And such types of and classes of vulnerabilities, they've been discovered like early 2000s and still suitable in modern firmwares. And as we can see, they not go away, and exploitation of them maybe became a bit more complicated, but not actually stop the attackers to still finding such bugs. And also I want to talk about another good thing. It is Intel initiative about bug bounty project Circuit Breaker, and binarily also been participating there. 20 plus advisories been submitted. So we have some scoring like widest impact for the binarily EFI Explorer team and most eligible reports for our submissions. But let's talk about actual vulnerabilities and where these failures are happening. To be honest, like sometimes even already known vulnerability can become multiple iterations problem. And as we can see, one of perfect example for this repeatable failure, it is USB-RT component, which is widely used on BIOSes, which has been developed on top of American Megatrends code. And it's not only desktop system or laptops, it is a lot of servers using as well such code. And as we can see, the first time when it's publicly discovered the vulnerability in USB-RT component, it's been 2016. But since that, we still can find the vulnerabilities in this component. And The reasoning why it is multiple components of this equation connected each other. One of them, it is a complexity of the code. And to be honest, it's hard to fix this code because actually the structure which is responsible for actually passing some of the data object from controlled by the attacker space to the SMM driver is just very, very big. It is like a few screens of fields in this object, and it's hard to protect and sanitize all of them. And also the developer can always do a mistake when introducing new code, but forget to copy and paste or develop like boundaries for this code or sanitization. And it's create overall like repeatable failures and introducing like new vulnerabilities in the same component. And it's just very hard to fix it. We really recommend to just removing USBRT if you have in your BIOS or in your firmware, if you are a device vendor, because this opening like a large attack surface. And we've been talking about USBRT vulnerability and new iterations of the vulnerabilities we found on our offensive talk. And we also demonstrated first publicly known ROP technique against SMM. It's demo available on internet on our YouTube channel. But basically, the thing is, it can generically bypass such mitigations as SMM code check and many others. But also, sometimes vendors can say, like, these vulnerabilities are not actual vulnerabilities already because they are being patched or basically this component out of support. But we're talking about supply chain, right? So it's hard if the vendor not supporting this component, it's a lot of devices in the field which still use this component, right? Or maybe these vendors who support the devices can introduce new code, which is can basically still available on based on USBRT on modern devices and modern BIOSes. And as you can see, like in this year, we disclosed in a collaboration with the Dell PCERT 3 new vulnerabilities, and thanks Dell team for making very quick fixes and actually remediate these vulnerabilities on their devices. But still such of the problem exists. But let's talk about the collisions in the supply chain. Basically, one of these perfect examples, it's overclock SMI handler. If you can see here is a classical out of bound write primitive where basically the attacker can control the write to SMM memory. Of course, it's lead to the arbitrary code execution, but problem is this vulnerability get fixed in the component which has been developed by IBV, independent BIOS developer, but basically not included the fixed version to the device package, firmware device package on the vendor side, on device vendor side at Intel, and binarily found independently this vulnerability. And actually this discovery, I would classify as a collision of supply chain. Technically, this fix being exists, but the device being still vulnerable. So we get CVE for that, and thanks Intel for collaborating to fix this issue. But to be honest, again, overclock SMI handler, it's very vulnerable component. It's been known for years as a very suitable attack vector. Binarily team opinion, this component should be removed to secure the firmware, because the complexity and the code, it's not very suitable for providing security capabilities in the firmware. Another issue, it is actually classical stack overflow with controlled by the attacker in VRAM variable. And basically, as we can see, this is platform initialization mode, which is executing on very early boot, and it's before SMM even get initialized. The attacker, if the attacker will be use this vulnerability, it's actually give them a lot of privileges, even more privileges before compared to SMM, because the attacker can influence SMM initialization and a lot of other things. So basically, this bug is very powerful, and it's been found on originally on platform init advanced premem component, and it's been patched by Intel. Here is a CVE number, and this vulnerability related to IBV code base. And what IBV means, Kai actually provide very good explanation. It is kind of like some sort of a reference code which is applies to many devices which is used this code base across of them. And if you found vulnerabilities there, it can attack not only single vendor, it can attack multiple vendors. Another very interesting vulnerability related to pretty new Tiger Lake based HP device. And this one actually been found as a part of the bug bounty with Intel and disclosed to Intel, but this leads some of the delays of disclosing to HP. HP introduced the fixes earlier than bug being reported to them, but basically binarily been discovering independently, and tomorrow it will be updated vulnerability report on the HP side. At least it's how it's been explained to us why this collision happens, but also as we can see, and it will be discussed later today, the collisions and actually earlier fixes, and we call this silent fixes, happening in many times. And sometimes even like the component can be removed with a fix, and by mistake or maybe accidentally for supporting some of the older features, it can be replaced with vulnerable component with an older version. So, and this vulnerability is actually also classical out of bound, it's classical memory corruption over SMM, so which is leads to the code execution, and it's been found on HP code base. So another one, it is classical get variable. In this time, it is a Dixie phase. So basically leads to the stack overflow. The attacker have like control on PCIe power management variable, and also data size. As you can see, it's initialized just one time and it is 0, but basically after the first time get variable call, we don't have initialization or reinitialization of data size, and it's just reused from the previous time, which is can lead to the classical memory corruption vulnerability. And such vector been discussed in many times already. We talked about that with Alex Teрешkin and Adam Zabrodsky last year on Black Hat US. Also, it's been multiple publications on binary block, and our plugin EFI Explorer can detect such problems automatically. So basically, as we can see, it is even more issues. We just discussed 51 and 52, 50 and 51, but here is two more vulnerabilities. And actually, it can lead to multiple failures in supply chain when the vendors deliver sometimes by mistake, or maybe just rushing to deliver the fix, the silent patches, when the patch doesn't contain the CVE. So it can mislead the understanding of enterprise companies, like what's the priorities to fix that, what's the impact of this security fixes, which is being just said by the vendor, this firmware contains security fixes, but which one? Sometimes it's not explained pretty clearly. So it's why it is very important to have all the components tracking about the CVSS scoring and vulnerabilities, because also it can be additional information and context why the developer need to pay more attention on that. And of course, like during the development phase, it can be happening multiple circumstances. As example, like as you can see on this example with binarily 2021-44, it is use of one of the EDK libraries called security package. And this static library just get accidentally compiled to some of the component, which is called trusted device setup app. and it's contain pretty suitable callout pattern, but fortunately for Intel device, this vulnerability and this driver not get into runtime with this callout code. So basically, that means this bug it's hard to exploit, but the primitive, vulnerable primitive, it's actually exist. And if it will be different environment, it can be exploitable, right? So it's just this particular device don't provide in runtime suitable environment for the attacker to reach this vulnerability trigger. Another example, it is actually vulnerability 2021-40, which is being patched by HP in March, but actually some variant of this vulnerability with different PCD number, just 1 byte difference, being patched a week after. Why is that happening? Because sometimes actually static source code analysis is failing because it's hard to identify this similar code pattern because it just contains different parameter, but basically it's exactly the same vulnerability. So basically we understand why it's been fixed without introducing additional CVE, because it's exactly the same vulnerability, but just different byte, which is doesn't actually related to the trigger itself. So if it will be providing additional capability for the attacker and triggering something, so of course it will be a different bug. But also very interesting situation with a compiler generated artifacts. And if you can see here, it's a few examples, which is showing how compiler can optimize the mitigations and security boundaries. That's pretty cool when you have like a size calculated dynamically, but compiler can think differently and just use a constant, which is suitable for this particular state of the code, which is when it's get compiled, right? And as we can see, this can lead for multiple problems when the boundaries, original security boundaries created by developer, doesn't meet the reality. And as we can see here, it is basically failing on validation of the boundaries, and write primitive can exist to lead classical code execution into SMM. So basically, we highly recommend you to not avoid the binary code analysis if you develop in the firmware, because it's very important to make sure what exactly code you are shipping to your customers, and does this code containing any additional vulnerability patterns on binary level, because it's exactly where you can find the truth and what you're shipping out of control to the customers, right? So, and we developed the EFI Explorer plugin. We actually been talking a couple of times on the Black Hat already and mentioning this plugin. It's open sourced and it's providing very powerful capabilities to reverse engineer UEFI firmwares. So also for detecting known vulnerabilities patterns, all the disclosures lead to the firmware hunt rules, and this actually introducing the new version of the firmware hunt, which is not only detect one variant of vulnerable trigger, it has some logical concatenation of multiple patterns and can trigger variants of the similar vulnerability patterns. But also, Richard will be talking about LVFS and talking how this working on at scale to protect firmware supply chain with the multiple vendors. Yeah, it's a small demo how firmware hunt works. We can see how fast it is scanning the whole firmware image, but also we want to cover very important topic, how the ecosystem is broken, but do we really have a fix for that?
So Alex has shown just how broken everything is, and maybe we can show you a solution. So LVFS is a website I created. It's the Linux vendor firmware service, and it allows hardware vendors to upload firmware updates to be distributed to Linux users at zero cost, both to the vendor and to the user. There are about 150 vendors, including Dell, Lenovo, Intel, HP, etc., using the service every day. There's about 1,000 different devices supported, and we've shipped over 51 million updates since we started the project. And we now average about 2 million updates a month, all deployed using FWFT client. As part of the conditions we agree with vendors is that we can take the firmware, we can decompress it into shards. So a shard might be an EFI binary, Intel microcodes, AMD PSP image, etc. And we can analyze it however we like using various rule engines, which sometimes includes decompiling the firmware into some sort of bytecode, which lets us do some cool stuff. So all of those vendors uploading all of those updates gives us a huge amount of data. This graph shows the results of analyzing over 9,000 UFI updates from about 800 different devices. And this shows the newest available Intel microcode for all of the different models on the LVFS. We can see about half the models are shipping microcode from this year or last year, which I suppose is good-ish. Of course, microcode updates are hugely important for the entire secure boot story. I guess second only to like ACMs or something. So many of these devices with old versions is really bad, especially since Spectre Meltdown was what, 2019, Platypus was 2020, and there was another CVE release just 2 days ago for a different speculation issue. And in almost all the hardware in the field is completely unpatched. So analyzing the 300 most popular CVEs, we can see some trends over time. Now, there is a lot to unpack on this graph. The x-axis is time, the y-axis is the delta between the embargo date of public release and when the update is available to install on the sort of end user customer machine. Each dot represents one update, with bigger dots representing more models covered in that release, and the different colors represent the different vendors uploading. The CV data is self-reported by the vendors and is broadly but not wholly accurate. You can see there are some big delays in getting some security fixes, with some users waiting 2 years since the embargo date. Go back. Might notice that in some cases the delta value is negative, i.e. the dot is below the 0 line. Some vendors ship updates before the embargo date, either by accident or deliberately. This is really bad, as it's trivial to decompile binaries and find out exactly the security problem that's being fixed. Interestingly, the diagonal line shows how manual the whole process is. Security team is patching the flagship models first, and devices nearing the end of life, being patched much later. In the data, you can also see delays due to national holidays like Golden Week and US Thanksgiving. I guess the good news is that the trend over the last 3 years is downwards, i.e. the vendors are getting slightly better at shipping updates in a timely fashion. So we can be cleverer. We can detect when vendors are fixing security updates, even if they're not tagging them with the correct CVE numbers. Using the firmware hunt rules developed by Benali, we can scan the EFI binaries and perhaps remind vendors that they might have misclassified the bug from an enhancement update to a security update. Working with CERT, we can use the Vince API to get the embargo date of public release and suggest to the OEM QA team that pushing the seemingly innocuous update would be breaking the embargo, or remind them perhaps the other way that it's been many months since the security issue has been made public. As more firmware hunt rules are created, this will become even more useful for OEMs and ODMs. So my personal conclusion is that only by working together with CERT and companies like Benali, we can improve the ecosystem even further, speeding up the process of shipping fixes to end users and making sure that security issues are patched by all vendors. These are really hard problems, and making sure security, and that they've plagued the entire industry for what, 20 years. And only now do we have all the infrastructure and the data to make things better. So I guess back to Alex to sum all this up.
Thank you, Richard. That's been amazing solution provided during your speech, and basically collaboration, it's a key to fixing the supply chain. And I want to say, like, fixing supply chain, it's a team sport. So only cross-industry collaboration and with the multiple vendors, it can help us to provide suitable solution for such problem. And also, I would say, you mentioned it already, working with the CertCC and WIN system, it's very helpful because we really need some sort of independent oracle, which is not a vendor dependent, to helping coordinating disclosure with a similar attention to multiple parties, right? Because when you disclose into one vendor, always vendor cares to patch themselves faster and basically as a courtesy collaborating with other parties. But that's not always works well with the industry-wide disclosures, because when the multiple parties involved on the disclosure, everyone have their different patch cycles, and it's became some sort of race condition when asynchronous nature of delivering the fixes by multiple vendors, it can create some sort of circumstances, which is actually Kai been covering at the beginning, when one vendor patch vulnerability, another didn't, and it will be lead to some sort of like window when already patched vulnerability still suitable 0th day for some set of the devices. And it's really why we need to collaborate better to fix supply chain problems and make patch cycles actually shorter and patch delivery more suitable and synchronized between different vendors. And as we mentioned it, like we have this open source technology called Firmware Hunt, which can be used for patching, for actually detecting already known vulnerabilities. And it works on the semantic level of the code, which is make much more suitable detection. It can detect the patterns, which is hard to, as example, create rule for detecting with Yara and other things. We need more tools to cover and protect supply chain. And I think Kai, Richard, and myself, we try to make this talk combine multiple problems in one way to deliver the message. We really need to collaborate more and fix such problem in supply chain. Thank you very much. And it's been a pleasure to deliver our talk on Singapore Black Hat Asia, this time virtually, but we open for question. Thank you. Yeah, just also I wanted to say we have 3 different time zones on the stage. It is London, it is Germany, Bochum, and Southern California, Los Angeles. So basically, we made it with all this desynchronization of the European time zone from Pacific time zone, and actually we need to sync with the time zone in Singapore. So Richard have a craziest timeline. It's like been 4 a.m. when we started to connect.
My alarm went off at 3 a.m. this morning.
Yeah.
So I guess we wait for questions in the chat.
Yes, I think so. And
I guess if anyone doesn't want to ask questions, like Benali is easy to Google, and obviously talk to Alex. From LVFS point of view, again, Linux Vendor Firmware Services, fwft.org. And I guess I'm friendly. And Kai, you're immune. So
yeah, you can find my email in my profile, right, on the website. Or just immune.ne. But yeah, thank you guys. What a nice presentation here. And I think if you guys watching our presentation, I'm not really sure about what firmware, right? And is it really that important? Keep in mind that we are pretty early in the firmware security space here. The problem will only become bigger, right? So the complexity of firmware is only growing. The amount of code down there is only growing. If you look at the bugs that finally found, these are more if you compare that with like Chrome, or the standard bugs in operating system. These are more low-hanging fruits. There are a lot of bugs in there still, a lot of surprises there. And I think if you're a defender, I think it makes sense to take this problem serious now instead of like 5 years.
Recent DHS report actually been saying for the critical infrastructure, firmware and device security became a critical point of failure. So, which is very important message, and we need to pay much more attention specifically in the areas where it's related to the critical infrastructure, medical devices, and some others. So we don't have questions in the chat, but basically like it's very important to cover such topics like firmware and device security. And I think the audience will be paying much more attention. But as Kai said, complexity only growing. And if you think about like modern UEFI firmware, it's much more complex than modern NTOS kernel on modern Windows operating system. Currently, the firmware image contain overall about like 6 million plus lines of C code, which is a lot. And basically, of course, C code kind of like pointing to the direction it can be vulnerable at some point and lead some bugs. And we see also the shift when some firmwares get developed on some particular drivers get developed on more safer languages like Rust. But still, because you can't just develop on safer language whole firmware, you need some assembly stops for early boot or something like that. It still have some window where the code can be vulnerable for multiple different directions. But thank you very much all. I think it's pretty much it from us, and see you next time. Hopefully in Vegas. Bye-bye.
Thank you. Bye-bye.